Hello, and welcome to Water Properties Part 2. I'm on my way there, and we've already seen all this. Here we go, Water Properties Part 2. All right, so in looking at water, water is considered the universal solvent because it can dissolve most things. So when we're looking at, let's look at some basic terminology. We have solvent, and solvent is the liquid that is doing the dissolving. So in this case, you'd have water is the solvent. The solute here is the thing that's being, the substance that's being dissolved. And so that is the solute. The solution is the substance that has equal distribution of the material. So this would be the solution. So once this is dissolved in here, it's called the solution. And then water itself, well, let's see what we got here. Oh, no. Okay, so water itself dissolves by pulling apart the salt. So the water is pulling apart the salt molecules. And it says, see the water forming shells around the sodium and the chlorine. So the water, see how the water is forming these shells around that. Okay, so it's in talking again about those hydrogen bonds are what makes this possible. And then remember that when we talked about polar versus nonpolar, and that polar is charged, and nonpolar is that it's not charged. So oils, grease, and fats are nonpolar, and water can't grab onto it and dissolve it. So there needs to be salt to make a molecular bridge in order to dissolve it. So dishwashing liquids are just basically salt water with coloring, because it is that bridge. It's going to tear apart that hydration shell that's around it in order to be able to get to the oils and greases and fats. All right, so going back to the we've already looked at hydrophobic. We looked at it once with studying the cell membrane, and we're back at it. When we were studying the lipids in the cell membrane. Of course, lipids are oils and waxes and stuff, fats. So hydro means water, and phobic means to fear. So this is a water-fearing substance. And water cannot attach to the substance because, again, this substance is nonpolar. So they do not interact. So the substance, this hates the oil hates the water. Okay, and salt is hydrophilic. Hydro meaning water, philic meaning love. So salt is water loving. And water can't attach to this substance because the substance is, it can attach to this because this is polar. All right, now we have this dissociation, and this is where it's going to break apart. So we have the water molecules. So we start off with H2O here and this hydrogen bond between these two water molecules. And what's going to happen is they're going to dissociate. So it's going to break apart. When it does, it doesn't break apart into water and water. It breaks apart into this hydronium ion. So you can see there's 3 H's here. There's 3 hydrogens here. And then this hydroxide ion, this OH minus. So you definitely want to know the difference between the hydronium ion and the hydroxide ion, what those two look like. And we're going to look at the pH scale. This is going to be real important as we go into and do the lab on the pH scale. But this breaking apart of water into protons, this would be a proton, and this would be a hydroxide ion. All right, now a proton actually is not the hydronium ion, it's the H plus ion, so it's going to split apart that way. All right, so here looking at the pH scale, the H in the pH is for hydrogen. And what it's doing in this pH scale is we're measuring the concentration of how many of these hydrogen ions are in a substance. So it's a measurement of those hydrogen ions. This scale goes from 0 to 14, and with 7 being neutral, and you can see along neutral there's pure water, and human blood is just slightly, it's about 7.3 as its pH. And so here on the pH scale, if it's less than 7, it's acidic, and if it's more than 7, it's basic. A real easy way to remember that is A, acid. A comes before B alphabetically. So we're going to find, on this scale, we're going to find acids before we find bases. Very simple way to measure it. All right. Now, buffering. A buffer is a substance that can resist changes in the pH or in the measure of the hydroxide ions. So buffering, this is an example of buffering by bicarbonate in blood. So the hemoglobin picks up the CO2 and this hydrogen ion, and then it transports it, and then it releases the hydrogen ion. So the human blood is a good example because bicarbonate helps keep blood at the pH of 7.4, or right around 7.4, 7.3. It helps keep that pH level. It's needed because the food, drink, or air, or other substances that we put into our body all have different pHs. And so this acts as the bicarbonate acts as a buffer. So the bicarbonate, let's see if there's no, it's not. So the bicarbonate is HCO3, and I'll write that on the board when we're in class. But it can take on a hydrogen ion from the blood to become carbonic acid, and that raises the pH level. Then the carbonic acid then travels to the lungs where it's converted to water and CO2, and of course we release the CO2. Or the carbonic acid can give off a hydrogen and become the bicarbonate and the hydrogen ion, and that helps to lower the pH. So it just depends on what the body is in need of at the time. All right, now we look at acid rain and this concept of acid rain. And acid rain, when we're talking about precipitation, we're talking about rain, sleet, snow, ice, fog, any of it with a low pH. So a pH lower than 7. 7 is neutral, and anything with a pH below that is acidic. Now, you know, it may not seem like it's a big deal, but it's huge. So water falling in the environment that has a pH of less than 5.6 is considered acid rain. And where that comes from is burning fossil fuels, so such as oil and gas, that put sulfur oxide or nitrous oxide in the air. When this combines with water, it becomes acidic. Of course, both of those are found in fossil fuels such as oil, gas, or diesel fuel. And so it forms, it combines and forms with the hydrogen that's in the atmosphere, and it makes an acid. And then when it rains, of course, now the pH of that water is now higher than, is lower than 7. And so that's going to cause a problem. It can burn leaves, it's going to put too much acid in the soil, and the plants are going to die, or it's going to have an impact, clearly, on those plants. So you can see these dead trees right here, and that's the effect of acid rain. That's coming because it's the water is just too acidic. And you can see on concrete, here's what it looked like before, and it just eats up that concrete because the water is too acidic. It's destroying it. And, oh my, it looks like that's all we have for today's show. I know you're so sad, but let's end it there, and we'll pick it up tomorrow.